Hello everyone, my name is Qingcai Jiang from University of Science and Technology of China. Today I am going to share with you our experience on accelerating parallel excited state electronic structural calculation by low-rank approximation. This is the outline of our presentation. First, I will give a brief introduction to Lrtdft. Then I will introduce our parallel implementation of Lrtdft, including theoretical algorithm and parallel implementation. Then I will show our algorithm innovations in detail. Finally, I will report numerical results and analyze. Linear response time-dependent density functional theory is a self-consistent framework proposed to describe the excited state properties in many systems like solid materials, molecular systems, and biological medicine, which has been widely used in metaphysics, quantum chemistry, and material science. Generally speaking, there are two ways to solve the time-dependent Schrödinger equation within the framework of Lrtdft, one of which is linear response time-dependent density functional theory, also known as Lrtdft. Within the Lrtdft framework, the most common way to obtain the excitation energy and corresponding wave functions is to solve the linear response Consider equation. The most time-consuming part in Lrtdft calculation is to explicitly construct the Lrtdft Hamiltonian with the ultra-high complexity. The challenge is how to make the calculation more accurate, larger, and faster. Accurate means we need to solve first principles density functional theory problem and use high-precision plane wave basis. Larger means we need to calculate tens of thousands of atomic large systems. And faster means we need to reduce the time cost. Generally speaking, the framework of Lrtdft consists of two parts, constructing the Hamiltonian and diagonalizing the Hamiltonian. Constructing the Hamiltonian needs to perform FFT, GEMM, and some numerical steps, and in the initial implementation, we use SYEVD routine in Scalability in performing the analyzing the Hamiltonian. In the procedure of Lrtdft, all numerical steps are based on the matrix PVC. PVC is the transpose block phase splitting product of valence and conduction orbitals in real space. It is a very huge matrix that can be thousands of gigabytes according to the physical system size. Let's brief on the complexity of each step in the Lrtdft calculation. As we can see from this table, the two main steps in Lrtdft calculation has ultra-high complexity of O(n to the power of 5 and O(n to the power of 6. In this table, Nr is the number of real space points, Nc is the number of conduction orbitals, and Nv is the number of valence orbitals. Then I will introduce our parallel implementation. We have three data distribution themes. One of these is column block partition for FFT. Because we need to transfer between real space points to reciprocal space points, and in reciprocal space we can perform multiplication instead of convolution, which can reduce time cost, and it is a standard procedure in density functional theory calculations. And another scheme is the row block partition for GMM. And the other is 2D partition for SYEVD routine in Scalability in diagonalization the Hamiltonian. We transform them via MPI auto or MPDGMR2D, which is a Scalability routine. Then I will introduce our algorithm innovations. When we look to the matrix PVC construct from valence and conduction orbitals, the information beneath it is commonly markedly redundant. In other words, we can use several small matrices to represent it. It is so-called interpolative separately density fitting. In brief, we can choose mu points to represent all points of orbital pairs, and mu is generally 1% of NCV, which means we can reduce the time cost 100 times theoretically. Then the question is how to choose mu interpolation points. One traditional way is to use the randomized sampling QR factorization with column pivoting QRCP, which solves the equation z pi equals to QR to choose mu interpolation points. But QRCP has two defects. It has ON cube computation time, and it is implemented with Scalability, which lacks scalability when the computation size becomes very large. To further reduce the expensive QRCP procedure in interpolation points selection, we propose a parallel k-means clustering-based interpolation point sample algorithms in Lrtdft. K-means clustering is one of the most simple yet effective unsupervised machine learning algorithms, which can reveal the underlying correlation of data. In this work, it means electronic correlation effect. By partitioning the real space point into k non-overlapping clusters according to their range of similarity. As we can see from this figure in the left is an example of excitation wave functions, and figure in the right is the projection of excitation wave functions and 15 interpolation points chosen by k-means clustering, indicated by the red dots. The centroid of a cluster CK is defined as the weighted average WR, and WR is the weight function for each real space grid point. In Lrtdft calculation with plane wave basis set, we define weight function as the norm of orbital pairs. And the below figure is the time spent in selecting interpolation procedure of Lrtdft calculation in seconds. As we can see from this table, the k-means algorithms reduce the time cost by a large margin. Constructing and diagonalizing the Hamiltonian occupies almost half of the total work-log time. According to Amdahl's law, to reach a desired overall speed-up performance, we also need to accelerate the Hamiltonian diagonalizing step. In general, the matrix H is large, and we always only need a few eigenvalues and eigenvectors. It means that instead of solving the entire diagonalization problem and extracting certain eigenvalues, we only need to find a specific eigensubspace of H with the smallest eigenvalues. To meet the requirement, we use a parallel locally optimal block preconditioned conjunctive gradient (LOBBCG) method, which is a conjunctive gradient method to solve the equation in the subspace. Although LOBBCG is the standard procedure in interactively diagonalization, but the implicit Hamiltonian costs an O(n to the power of 4) memory footprint. We notice that combining with Lrtdft decomposition, the H can be always keep a factor form. After changing the order of calculation, the total computation cost of implicitly constructing and diagonalizing the Hamiltonian can be further reduced. The complexity after each step is summarized in this table. As we can see, implicit K-means ASDF LOVBCG version significantly reduce the computation and memory cost by nearly 2 orders of magnitude. Then we will introduce a pipeline approach of GMM and MPI reduce. First, let's look at the figure in the above. First, by analyzing the data partition of Lrtdft, we find that in order to calculate the difference between the energy eigenvalues of Qingcai function, not all MPI tasks need to store the entire VHXC matrix. Therefore, we optimize the data partition method shown in the above. Then we get the result of GMM. Each MPI task only need to store a part of the matrix. As a result of this attempt, we have eliminated part of the data dependence. In more detail, we can divide the matrix into small pieces and manually perform GMM to these small parts. The basic flow of GMM and reduction is shown in the below. Once the result of each block is obtained, we can immediately reduce the block matrix to each MPI task through MPI reduce. Then we will allocate the entire VHXC distributed in each MPI task. The testing system including two parts, cubic silicon system and metric angle twisted bilayer graphing with 1118 atoms. For cubic silicon system, we use various choice of crystal silicon system with 44, 216, 512, 1000, 1017, 2700 and 4000 silicon atoms. All numerical tests are performed on the National Energy Research Scientific Computing Center's core supercomputer. We run our code on the hardware partition, whose each node has 2 sockets. Each socket is populated with a 16-core hardware processor and 128 GB DDR4 memory, and we byte for OpenMP threads per MPI process. We first analyze the numerical accuracy of our code. We compare our naive version code and implicit K-means ASDF LOVBCG version with the current state-of-the-art software Quantum Espresso QE, which serves as an accuracy benchmark. Due to the back scalability of QE, we only use water and silicon system with 64 atoms as our benchmark. This table lists the results. We found a good agreement between the result of QE and Lrtdft, with a small difference in excitation energy for an identical order of states. Our optimization will only introduce little error as small as 0.001% in relative error, which is fairly negligible. These results means that we already dismiss almost all redundant computation costs beneath Lrtdft calculations. The most significant measure for Lrtdft software with all these aforementioned optimization is the strong scalability, which reflects how much the growth of hardware resource take effect for a determined system as adding the number of computing resources. The parallel efficiency of our naive design maintains above 50% when scaling to 2048 processing cores. This result is quite acceptable among Lrtdft calculation with plan-weight basis set, since we need to do a series of collective communication in the global domain. Also, we give a more detailed analysis by splitting the workload time during the procedure of constructing the Hamiltonian into 4 parts: K-means, FFT, MPI, and GMM and reduce. As figure in the right shows, due to our parallel design, the K-means GMFFT and even MPS procedure maintain a very convincing strong scalability performance dear 2048 CPU cores. But to implement the implicit method, we transfer the HC integrals from a single GMM operation to a series of GMMs and an MPI or reduce, which hinders the total time speedup for idea. Since MPI collective communication routine will bring in extra overhead. To maintain good speedup and scale the system to a larger size, the implicit Hamiltonian method is indispensable. So this method is a trade-off between efficiency and strong scalability. But in our test, GMM and reduce step only cost 12% of the total time of constructing Hamiltonian. The small sacrifice of strong scalability is quite acceptable. We also perform tests to validate the speed-up ability of our method. We further reduce the computing resource and bind a single core to an MPI process. Thus, each process holds only 4 GB of memory. We evaluate tests on different sizes of systems with naive IS and Lrtdft LBBCG version. We observe an average speedup of 9.3 times, which is quite convincing. In fact, among all of our numerical results, the average speedup under our optimization is over 10 times. Combining the accuracy property, our method can reach quite faster calculation with fewer computing resources. In this work, we propose several optimizations to accelerate Lrtdft calculation without little accuracy loss. In our experiment, this method can gain an acceleration of about 10 times while preserving admirable accuracy. Given all these benefits, we can push the envelope of first principle excited state simulation further. Thank you.